afternoon, everyone. So today we're going to be looking at virtual commissioning with MapleSim and the connection to B&R Automation Studio. So just to start, what is, a bit of an overview of modeling with MapleSim, just for anyone who maybe hasn't seen MapleSim before. It is a system-level multi-domain modeling tool. So what this means is we're going to be looking at not so high level where you don't have any real physics embedded within, and not so low level, not on the level of say an FEA or CFD. We're kind of in the middle, multi-domain, because we can obviously mix different domains. So mechanical, electrical, hydraulics. And we're going to see an example of that in today's webinar, where we actually have a hydraulic system, but there are also some 1D mechanical pieces involved as well. Once we build our model in MapleSim, which is the modeling and simulation area, we can then use Maple to do analyses. There are built-in apps to kind of get you started in looking at different aspects of your model. And once you kind of maybe fine-tuned it or you're happy with the analysis that you're seeing, you can then export your model as an FMU or C code. And in today's webinar, we're going to be looking at an FMU, but a very specific FMU that is generated for B&R Automation Studio. On this screen, you can see that there's a reference to MapleSim Insight. Typically, this is used to view the 3D animation associated with an FMU. But as you'll see today, when we do this connection to a B&R Automation Studio, there is a visualization that is available for the FMU through Scene Viewer. Just to give a bit of context as to what we're really trying to do with our virtual commissioning. So typically in the physical or the real world setup, you're going to write some code in Automation Studio. So this is your control logic, all those steps that you want your machine to take. And this is where you're writing your PLC code. So you then take all of that code and you're going to transfer it to some target in the real world, some kind of physical PLC. Right, you might have many of these embedded within a single machine. And then once you have this PLC connected, that's really communicating with the robot. So in this example, maybe it's some kind of robotic arm. It has sensors passing information to the PLC and then receiving data in terms of, say, how much torque to give to a motor. Maybe it's an electrical signal. There are really different options, but the idea is always the same. You're kind of passing information back and forth between your machine and some physical PLC. Now, today we want to talk about virtual commissioning. So it's how do we take this real world setup and kind of mimic it in a virtual sense? And then obviously the benefit of the virtual machine is you can try to test new scenarios, new ideas without the fear of really damaging your physical hardware. So let's look at the virtual commissioning setup. So you're still writing your PLC code in Automation Studio. This part doesn't change. What really changes is going to be your connection points. All right, so you're not going to be sending information. You're going to be connecting through a different target. So in this case, we're going to be going to a standard PC. I'm just going to build it on here. Of course, you can test this on different targets. For this webinar, I'm going to be using a standard PC. And this is going to be, quote unquote, my new PLC. Now I'm going to be able to transfer information back and forth between the model I made in MapleSim that I was able to export as an FMU and import into Automation Studio. So now what I've done is I've replaced that physical machine with my digital one. And I can still send signals to it as if I were connecting to the real machine, just through a slightly different path. So just a bit of a summary, and then after this, we're going to jump into the example. I want to spend most of my time today really going through, beginning to end of the entire process. So for our virtual setup, we have MapleSim, our system-level equation-based modeling tool. We're going to generate an FMU with a specific app called B&R FMU Generation. And again, this is an app that creates an FMU that is essentially ready for import into Automation Studio. There's no real work or additional work you need to do, and will allow visualization information to be also read in. B&R Automation Studio, again, where we're going to have our PLC code, obviously can connect to different targets, and it's actually Automation Studio that's going to perform the simulation of the FMU. Finally, we're going to look at B&R Scene Viewer, and that's going to provide us a 3D visualization of the model while we're running our simulation in Automation Studio. So in today's example, I'm going to go over an injection molding machine. So I'm actually just going to leave my presentation now, and we're going to jump into our MapleSim model. So again, just a quick overview for anyone who is new to MapleSoft products, specifically MapleSim. This is MapleSim. This is that modeling tool that I was referring to. On the left, we have various libraries that come with the tool. The ones that we're really focusing on today are hydraulics, since we are working with an injection molding machine, and it is driven by hydraulic circuit. And we do have multibody, which is representing more or less a mechanical domain, electrical, and these are all different domains that you can connect in your model. Right, so as I expand these different sections, I can see the components I can bring in. And on the canvas, which is this middle part, this is where I can actually build my model, make those connections. Here I have a subsystem for my injection molding machine, essentially representing that plant or that machine that I want to have a virtual version of. So I'm going to double click just to go inside and give a bit of a sneak peek as to what's going on. Let me just move this a little bit. So we can see in the middle here, we have our various hydraulic components, right? We have our DCV, we have our various relief valves, and then we have some kind of cylinder. So this is really what's driving that linear motion of the machine. I'll run a simulation just so we can see what it looks like in action. Again, to get the 3D visualization here, I've used the CAD toolbox. So I've imported a CAD file, and that allows me to bring in all the mass and inertia properties and really gives me a much more accurate simulation. Because this is equation-based and physics-driven, you really want to make sure those masses and inertias are correct, otherwise your results will be off. Once my simulation is complete, I can see my results in the results manager. So here we'll just see kind of, essentially what's going on in the system. So I have a reference point that is essentially moving from open to close. I have a very simple P controller, so just a proportional controller that's going to be used to kind of open or move the position of that DCV valve to really determine, how fast or how slow, really trying to track that position, which you can see in this first plot up here. So I have my set point in red and my actual position in green. So they're matching quite nicely for this simple controller. Other information I can pull from the system. I have my pressures, so on my A and B side, my DCV signal, the RPM for the motor that's driving the pump, moving all that hydraulic fluid around, and also the speed of my platen. In this case, the platen is this moving piece. So if you hear me referring to moving platen or the platen, I'm really referring to this piece that's really that section that we're trying to control. So this is the model that I say, okay, I'm happy with it. I want to be able to export this to Automation Studio, and that's the piece that I want to have as that virtual piece inside of my PLC code. So I'll go back to my canvas, back to my MapleSim. Maybe just to recap one little bit here. So we do have this multi-domain nature. So up here, these are my multi-body components. They are connecting to some 1D translational pieces. So this is things that just have 1 degree of freedom in that translational axis. And then there are always components that allow me to connect 2 domains together. In this case, that's my double acting cylinder, right? So we can see it obviously can only move linearly, but it's being driven by whatever's happening in the hydraulic portion of the system. So that's these red lines here. And if I scroll down, I can see here I have my pump, and this is going to be connecting my hydraulic portion of my model to the 1D rotational. Of course, it's just a motor, so there's 1 degree of rotational freedom. And that's where that whole RPM and setting that value for the pump came in. So what I've done is I essentially encapsulated my model inside the subsystem, and this makes it very easy to define what are my inputs and what are my outputs. Whatever I define as my inputs and outputs, these are going to be the same inputs and outputs of that FMU that I generate. And that FMU that I bring into Automation Studio, for those of you who are familiar, it's just going to be a function block. So it's going to have Joe's inputs and outputs, the same ones that I defined here. I'll go up one level back to that top screen. just so we can see exactly, what are my inputs, what are my outputs. So again, I have one input, which is my command signal. Again, that's for that DCV, really telling it between 1 and -1, whether you're in, in the one position or in the other position. And then my outputs, I'm measuring my plant position. So this is my current position. Inside of here, I've embedded what I want my set point to be. Maybe not as common. Typically, you might have something already predefined, kind of living in your PLC code. It works out to the same. I've just put it in here mostly for convenience in programming the PLC code in Automation Studio. And then these three outputs are really just things I want to know about my system, performance-wise, pressures, powers. Again, because this is a virtual machine, you can add as many sensors as you want in any location. And that's one of the benefits of having that a virtual machine. In a physical system, you're often limited to where can you actually add a sensor without really affecting performance or actually being able to get reliable results. So with a digital version, you can add sensors anywhere and really get a full understanding of how your system is behaving and how it's performing. So we'll go ahead and say, okay, I'm great. I'm happy with my model. I've tested it. It's looking wonderful. Now I want to export it from MapleSim. So all I need to do is on the left-hand side, this final tab are the apps and templates. And I'm going to navigate to the B&R connector and the Automation Studio FMU generation. So I'll double click to open up this app. And I need to select what subsystem do I actually want to export. I could select the entire main would be the entire model. But again, I just want to select that plant, everything that was in that subsystem. I'll hit load. All it's doing right now is it's connecting to my MapleSim model, bringing in all that data. And then I'm going to be able to see kind of a summary, the inputs, the outputs, various parameters. So I go on inputs. I can verify, yes, command is an input I want. Outputs, I have those two pressures, position, set position, as well as power, perfect. I can go to parameters. And here there's going to be just a couple options that you can choose. So you'll notice that as I select different parameters, there are three options on the right-hand side: none, fixed, and tunable. And this has to do with whether or not that parameter is going to be visible to you once you bring in the FMU in Automation Studio. Typically, you want to keep some things fixed, which means they're just going to kind of remain as is in the model. Maybe things like your fluid density. It's not going to change. You're always using the same fluid. It's better to not make it visible so that no one changes it or plays around with it mistakenly. However, there are some that we might want to change. In this model, I do actually have a parameter for an additional mass on that platen. Remember that platform or that piece of metal that's moving back and forth. I have a parameter that allows me to add mass kind of as I want, because that would give me the chance to see if I increase the weight, decrease the weight, how does that change performance? So all I need to do is select the parameters I want. So in this case, that add M, I select it, set it to tunable, and tunable means I'll be able to tune it or change it in Automation Studio. At any time, I can see a summary of all my parameters and their types. So in this case, tunable, I have one. Fixed, I have some other ones. And then these other ones are kind of more for filtering. But this is really the fixed and tunables are referring to which ones have these options selected. Then the last real section that I care about is the export section. And this is where I need to send or specify some solver information. The way that MapleSim packages FMUs, we actually embed a solver within it. This means you can bring the FMU to a computer or to a system that does not have MapleSim installed, and you can still run the FMU. This is different from other software companies will have different approaches. Some will embed it, some will not, meaning that you'll actually have to have the system with the software on it so that you can actually run the simulation because it will communicate to it. However, having the solver embedded does make things a lot easier. It can really just kind of speed things up and not force or not have you run into more problems. In this case, the way I'm going to pick my solver settings is I'm actually going to look at my model. I've been playing with my model. I've been playing with the solver settings, which are in this wrench icon on the right-hand side. And I found a set of simulation settings that actually gives me results that I'm confident with, right? So I've done some kind of convergence analysis. I know my results are trustworthy. And I found that this works well with my implicit Euler solver and a step size of 0.1 milliseconds. So I'm going to go back to my app. I can either go from the window here, or I can click this little tab up here. Right, so I want to duplicate those solver settings. So I'm going to pick implicit Euler. And this task class cycle time, this is not referring to the time step that you want the solver to take. This is the communication time step you want to have in Automation Studio. So in Automation Studio, I am going to run my program with a 1 millisecond step size for that communication. So what I need to do to ensure I have that 0.1 millisecond step size for my FMU, I'm going to expand the advanced FMU settings. And then for the number of internal steps, I'm going to enter 9. And we can see now that the internal step size is 0.1 milliseconds. So essentially what I've done is I've told my FMU that every time you get something communicating with you, it's going to happen at every 1 millisecond. And in between each of those communications, you need to take 9 steps. And so it's going to ensure it has that same accuracy that we were seeing in MapleSim. This is the only advanced setting I'm gonna change. The other ones can, they don't need to be tweaked in this model. They're a bit more advanced ones. Typically, we shouldn't have to change them. They should be, the model will be able to run without changing too many of the advanced ones. So we'll focus just on these internal steps. Now the last step is really just to generate this FMU. So I'm gonna navigate to my desktop just to make it easy to find. And I'll take out this one, I'll just call it plant. And I'll hit generate FMU. So we can see down here that it's evaluating, it's just grabbing all the settings that I put, kind of generating that code, and it's going to create the FMU for me. So, and I'll just navigate to my desktop, bring the FMU to make it visible. Of course, the FMU generation time can depend on the size of the model. This one is a bit, I wouldn't say it's a very large model, but it's on the slightly larger side, so it does take a bit of time. There is some optimization that's going on, which also adds to why it seems like it's taking long. But you'll see once we're running it in Automation Studio, we can run things in real time, and so that's the benefit of you pay a bit of a price here, but then you get something that's highly optimized, something that will run real time that you can use in Automation Studio. Right. So once this is done, I just get a .fmu file. So here it's just my plant.fmu. And because I use the B&R Automation Studio generator, I can just directly bring this into Automation Studio. So I'll open up the software, and I'm going to start this from scratch. So trying to give a bit more details versus just bringing it in and kind of hoping that everything, or showing that everything just works. I want to take it step by step, really make this useful for anyone who's trying to connect. So I'll call this project injection molding, keep this default configuration. As I mentioned, I'm going to use a standard PC for my target. So now it's going to set up the files for me, just kind of all those basic configurations. There's not much I need to tweak for this simple program other than I need to make sure that my cycle time is that 1 millisecond that I had when I was generating that FMU. So I want to make sure that that's still synced up. So I'll double click on my hardware, just open up the settings. By default, my Automation Studio puts programs in cycle number 4. So I want to make sure the cyclic number 4 has that 1 millisecond time step. So I'll right click here, change the properties. So first I need to change my system timer because it is greater than 1 millisecond. So I make that 1 millisecond, go to my resources, go to my cyclic number 4, and again, change that to 1,000 microseconds. So I'll save this, right? And now I can see my cyclic number 4 has my 1 millisecond. Great, that's the communication step that I want. So now I really just need to bring in my FMU, and I need to emulate that simple P controller that I had in MapleSim. So just a reminder, in MapleSim, I have my plant. This is what I'm showing, or what's selected is what I'm bringing into Automation Studio. And this is what I'm going to have to replicate. This P controller that is determining what that command signal should be. So I'm going to go back to Automation Studio. And then in my libraries, I'm just going to select, let me just move this over. So I'll filter by library. And there is this FMU library. So we double click. And all I need to do is navigate to this is my desktop. And so I'll pick plant, open this up. And there is a checkbox here for add FMU usage sample program. This is not necessary. You don't have to import it. I will just to show you what it looks like. It really just gives you kind of a reminder of what, how the connection should be made or the calling sequence. So I'll expand my plant FMU. So we have our library and the program. So I'll start with the program. It's very simple. I open up the cyclic part. And really, this is all that's happening. So as I'm going through my code, of course, there would be a lot more going on, different calculations. But the first step is I update my FMU, so that function block that's representing my plant, the actual code. This says take a step in time in terms of simulation. Then I want to pass visualization information back and forth. And once I've done that, I want to update my visualization piece. This piece is not necessary unless you want to actually see the results in Scene Viewer. If you don't, maybe you're happy with it and you want to keep your code as light as possible. These 2 lines of code are not necessary and they're just for visualization. So this is the default program it gives you. It shows it in C. Today, I'm actually going to program in structured text. So I'll close this sample program. And then, of course, in our library, so this is our FMU library. There's this other folder, and this is where we can see the plant.scn. And this is our Scene Viewer file. And if I double click it, it'll open up Scene Viewer for me automatically. You can download Scene Viewer from B&R's website. If you just search for Scene Viewer, you'll be able to find different versions. I'm using Scene Viewer 4. So one thing I'll do is I'll just change this view just to help me out with the lighting here. So we see it's the same visualization, that same representation I saw in MapleSim, and I can see it in Scene Viewer. So that's great. I mean, that's really the whole, or one of the main points about this whole connection that we have between MapleSim and Automation Studio. So now I'm going to go and write that code, and once it's simulated, just like we did in MapleSim, we'll see this moving back and forth. So for now, I'll just minimize this. And now I need to write my actual program. So I'll go to my top level folder, take off of this filter, and I'll go to my program. And I'm going to pick a structured text all-in-one. And actually in my software here, I'm going to disable this plant program, that default one. I don't really need it. I'm just going to keep this one, which I will also rename. And I'll just call it injection. I'll just call it injection. INJMOL. Keep it simple. Also want to keep the name small so that when I'm referring to when I'm trying to connect to this actual program, of course, if you have a name that's quite long, it does get truncated here. So this is the name of my program. I need to define a few variables first. So the first one is it's going to be my actual plant. So again, I'll just call it injection molding, or short form of it. Now, I know that the type is going to be plant, which is just the name of the FMU. However, if you actually click and look at the different types that are available, you can actually find it by looking at the function blocks category. Again, as I mentioned, the FMU does get brought in as a function block. And here we can see the plant and the plant view data types. And it's showing where it's coming from, right? So it's libraries, plant FMU, which we can see here, plant lib. So it is just that FMU we brought in. So I'll have one piece that's representing my plant. I'll also add my view piece, put a capital I to be consistent. So view, just to make sure that I know it's my view piece. And of course, I want to actually be able to calculate a command signal and send that to my FMU or to my plant. So I'll add my command, and I know that this will be just a long reel. So for now, these are the 3 variables that I have, and now I just need to write the code. So I'll go to my main, and I need to initialize certain things. So the first one is, if you recall, there was that add m, that parameter for the additional mass of the CAD. So I'll add this and I'll just set this equal to 0 for now. I'll zoom in for everyone. Right, so then same thing, I want to make sure my command, I'll just initialize this to 0, which is kind of a closed position. So not allowing any fluid, any hydraulic fluid to move between the various lines. I want to enable my FMU, right? So again, all of this is related to my actual plant model. And then I also want to enable my, my view piece. So I'll go injection mold view, enable, 1. So this is all I need to initialize. And now for the cyclic part, of course, I need to calculate what my command should be, that command signal, and then I need to send it. So in this case, I'm just going to replicate exactly what was in the model, which was just a simple P controller. In this case, my proportional value is just 0.1. And I'm going to calculate this by pulling information from my plant model. Right, so I have my set point, and I want to subtract from it my actual position. And this is kind of showing what you injection mold. Let me just find my variables here. And it is set point, plant position. There we go. Right, and you can see from here how, normally in your PLC you might be pulling data from a reference that is an actual machine, and all you would need to do is really substitute that with pulling the same data from your digital version. And so by doing this, you can really make the transition between having a communication between your physical code or your physical machines and your virtual one, kind of a one-to-one. So you sometimes we see customers, they'll put in a Boolean to indicate whether or not it's kind of digital mode or not, and then they'll just toggle between when they pull from certain data, whether they do it one way or another. But this is really the idea. You don't want to have to rewrite all your code. You just want to make minor tweaks to the entry points of when you're calling certain things. The other thing I'm going to do is I'm going to add a kind of a bound on my command. So of course, it's possible that this goes above or below 1, but my command input for my model is expected to be between 1 and -1. So I will just cap this by adding a min and a max, right? So the max of my command in -1 to make sure it's always above -1, and then the min of that result and 1 to create that upper bound. So this is how I calculate my signal, and then to pass it along or to make sure that it's going to get sent to my plant, I just have to say that, okay, my command value is just equal to that CMD. And I always want to set these values before I take that time step or before I call, an update on my plant. So before I actually write this piece of code here, which is just to update my plant, any inputs that I want to modify should come before it. Then I take a step in time, I get my results. So of course, I want to have that visualization piece. So just as we did in the sample program, we now need to make that connection between passing that visualization information back and forth. So the view piece, maybe just to make it more obvious. So this view piece does have an input called it's instref. It's basically just a reference. So I'm going to set that to, and I'm going to grab, there's an equivalent output from the plant model, right? Same name, but you can see here it's red. So it's got that red kind of box. So it is an output. Same idea as that sample program. And then of course I want to update my visualization piece. So now this is everything that I really want to do. I'm not going to add anything for the exit. So hopefully if I've done everything correctly, I can build my project and then get it connected to Scene Viewer. So I'll go to project. I'll just do an offline installation. Let it do its thing. It's looking good so far, no errors. It should ask me if I want to transfer. Perfect. Close this. And to see if it's running, I'll just add a watch on my program. Go here. And right now I just care about my command signal, maybe some values from my actual plant, right? So those pressures, that power, the things that I'm interested in. So I'll add those in. And we can see the numbers are updated. So that's always a good sign. It means something's something's running. What I'm looking at here is really my set point going from 300 to 0. And then my plant position obviously should be tracking that. So it looks like it's going back and forth nicely. So now my next step is to really connect to Scene Viewer. In this case, we're going to do it through PVI. So first thing I need to do is make sure my options are correct. So the task name, in this case, it's the name of my program. So it's the injection mold. So the same name here. The variable name, I need to give the name of that variable in my program that represents the visualization piece. So in this case, it's that injection mold, but with the view, right? So those should be the only two things we need to change. We'll hit OK, and then we'll hit connect. And just like that, we can see it animating. So again, if we look at the position, so it's near the 0, which is the close, heading towards that 300, which is 300 millimeters. So it is going back and forth. So we can see we have our system connected. And I mean, this is really the benefit that we're bringing in terms of connectivity to Automation Studio. You can not only get a realistic or a reliable model in MapleSim, something that is equation-driven, physics-based. You can med the solver, so you see it was very easy for me to bring in my system and start writing it in Automation Studio. And there's nothing better than having those visual debugging cues. I mean, sometimes it's nice to see traces and see the values as they're updated in a watch window, but it doesn't always paint the entire picture, especially if you're trying to maybe show an idea or show a concept to someone else. Having a 3D piece can really be beneficial. And maybe just to highlight the point of, okay, well, it's nice, it's running, but I'm essentially running what I had in MapleSim, so it's not, terribly exciting, so to speak. So now what I want to do is I want to add some kind of additional flexibility in the code. I'm going to introduce a K parameter that's going to represent the proportional value in my controller. And then I want to be able to play with it. And that's really going to give you the sense of, okay, here's why that visualization might be more useful. So I'm going to go back to my code. And what I want to do is I want to add like I mentioned, a parameter or a variable K, which I'll initialize to 0.1. And I'm going to set this value here. And of course, I need to add this as a variable here. So we'll add K. Again, this will be a long real. Right, so all I've done is I've introduced an additional parameter, and I'm going to play around with this K value, and I'll be able to see not only with those results in the watch window, but also visually to see, how does my system change in terms of response as I change the value of K. So I'll have to rebuild this. I'll just do a offline installation. Let it go through all those steps again. All right, we'll go to our watch window, let it connect, and I'll add that K to the watch. All right, so we see it's at 0.1. So of course the results are going to look the same as before. But maybe I want to change it. Maybe I say, let's see what happens if I reduce it. And I'm going to go a little bit extreme here. But actually, I'll wait till this. I'll just open this up, just make it a bit bigger, easier to see. Perfect. So I will change this value here, make it smaller. Sorry. All right, I'll wait till it opens, change the value. So let's see. So if I make my K, that proportional value 0.001, of course, now what I'm really doing is I'm reducing the size of that signal I'm sending to my DCV. And we can see that in the command here. So it's not changing maybe as much as it was before. So it's really having a hard time to open up in such a way that it can actually track the motion. Maybe I bring this up, a little bit so we can see, okay, great. So 0.1, and we see the issue with having that 0.1 is it's not going to quite close properly. So it is now moving more, but we're not quite getting to where we want to be. Right? So maybe we say, okay, well, maybe 0.1 was too small, I'll make it 0.5. And now we can see, okay, it's closing quite a bit, but is it closing too much, right? So now the question is, okay, are we actually slamming the platen into the other piece? Of course, we could see this through the, by looking at the plant position. We'll see that in this case, it actually goes negative, which it didn't before. That negative is indicating it would be slamming, which, I mean, these injection molding machines are quite large. And if you slam this plant into the stationary piece, it's quite a loud bang. So this is kind of the idea, kind of the advantage. And of course, in this case, I'm really just playing around with this simple P controller. So it's not, you know, it's not that it's limited to this, but this is the idea of what you can do. You can bring in this system, and you can really design an entirely new control strategy and test it on your virtual system. And all of this before you even deploy to the physical machine, or you can even do all of this before the physical machine is even fully built. If you know the designs and the specifications, you can still model it in MapleSim, bring your digital version, and run all of these tests. So that can really save a lot of time in terms of development, meaning that you can test strategies before you actually try them on the real machine and have confidence that this new strategy you've come up with should perform well once you go to that physical machine. And then maybe the last point here is there is that add M, that kind of additional mass that is represented as being added here. Of course, because it is tunable, I could change it here. It's not unreasonable to add, 1,000 kilos, 2,000, even 10,000 kilos. Just, I mean, some of these forms are quite heavy. This is essentially a metal form. One of the challenges is, of course, not all the parameters when you change them are going to kind of play nicely with the entire simulation. So for example, if I decide, okay, well, I want to make this now 5,000 kilos, because my system is running, it's going to be quite sensitive to this sudden change. I mean, this is quite a large change, right? So we can see that it kind of wobbled a little bit. In some cases, the simulation might run into an issue where it might fail. In this case, likely because of the timing of when I sent it in, it didn't run into any issues. But it is something to be aware of, that the model is still sensitive to abrupt changes. And so changing these tunable parameters while it's running can sometimes cause things to fail. So just something to be aware of. If you want to, say, run a separate simulation with a different value, of course, you can go to your code, change this initialization value. Your code will start up with this larger mass value, and we'll go from there, and will likely give you less grief. Let me just go back to my watch window. Now I'm just curious whether or not I can actually show the behavior I was trying to explain here. So I'll let this open up, see if I can, it should be stationary. Yeah, so now it's running into a problem because I changed it kind of mid simulation and I've run into a problem. So now we see that something caused an error, but it's not to say that I can't run the simulation with 10,000. I mean, I'm able to do it in MapleSim. So if I change this value to 10,000, again, I can rebuild it. And then this way, I'll be able to actually see my results for a mass of 10,000. It's not that having this mass caused the issue, it's changing it mid-simulation. Again, just trying to give some tips for people who maybe are trying to work in this space. So we're seeing it's building, it's going to connect. Then once it's connected, I can see my mass is 10,000. And then the visualization piece is back. And we see it's running without any issue. One thing to note here is, again, this is all part of that investigation. So now that I have this additional mass, maybe you have an operator that's asking those what if questions of, well, I have a new prospect that they want to have a mold that's going to add 10,000 kilos. Okay, great. Well, for our current control strategy, if we look at the plant position, of course, we want it to stay positive. And in this case, we're going to see it's going to go negative. So we are actually slamming into that other stationary piece. So again, this is the benefit of, we can play those what if scenarios and say, okay, we need a slightly different control strategy. Maybe we need to increase our K. I'm actually not sure how to, what the right strategy would be. This is now just kind of me playing around with it, trying to see, what might work. Would 0.5 help? It seems like maybe it didn't help it too much. So maybe that would indicate, okay, my simple P controller is not going to be sufficient anymore and really need to reevaluate strategies. So this is really everything that I wanted to show today. From start to finish, we created a MapleSim model. Obviously didn't spend too much time building up a model, but went over it Of course, it has the hydraulic pieces, your pump. It's moving things in a linear fashion thanks to our cylinder. We have some masses connected and our 3D visualization coming from CAD that we imported. We then exported this as an FMU using our B&R Automation Studio FMU generation app. Once we did that, we went to Automation Studio, imported this as an FMU library, created this folder here. Once we brought this in, we then had a function block we can use in our code. In this case, we created a structured text program. We were able to bring in our injection molding machine in this manner. Once we created all of our code and actually transferred all the code to our target, we could then click on the scene viewer file that was inside of that plant library, connect it, and actually see the visualization as we run our simulation. So I'll just finish up with my last slide here. Okay, so we did our demo. And just to wrap things up, so upcoming webinars. So in May, we do have a repeat of our inverse kinematics, industrial robotics, and manipulators. These are all coming from it. It's a very interesting topic. Inverse kinematics is one of those areas where MapleSim can provide a lot of benefits. Those questions of, if I have an end effector and I want it at a certain position, what angle should I have? Those kinds of problems can be tricky to handle or to solve manually. And so we'll have someone going over how to do that kind of more programmatically using symbolics in Maple and MapleSim. And then for anyone looking for additional resources, we do have our MapleSim model gallery, which is available online. Kind of shows different areas, different domains that you can actually model with MapleSim. If you have MapleSim, there are also models available for download from the model gallery. We also have online help for all of our Maple and MapleSim. So if you're looking for specific features, maybe you're thinking about purchasing, you can go there, search online from our website, and see all of the documentation. And then finally, we do have Maple Primes, which is our online kind of discussion board. A bit more focused on Maple, but there is an area for MapleSim questions, and so you can go there to kind of see, what's going on in terms of Maple and MapleSim.